stars. So tonight we're on episode 3, and there's really 3 things that I want to address. One is, how do astronomers classify stars? When you look up the starry sky, you'll see pictures, it just looks like a zoo of stars there. So how do they classify stars? How do stars evolve over the passage of time? And you may have heard of the Hertzsprung-Russell diagram. So what is that diagram and what does it do? What's its importance in astronomy? So for the format tonight is my chat first, about 35 minutes, but we all know I go over time, but so I'm doing my best. Then there's the video lecture, about 32 minutes. And I put this in here so then you can plan in terms of if you've got to go and catch a train or a plane or something. Then we'll have question times after that. And then we just got a little some homework, you know, for you to get most out of the talk. I thought let's just give you something you may want to do when you get home related to it. And then I'll briefly mention what's on next month. Okay, so tonight, key take-home messages will be: stars are classified by their temperature, how hot they are, and by their luminosity, how bright they are. Stars evolve over the passage of time, and here's one of the key points of tonight. It's the mass of the star that determines how it evolves and when it evolves. In other words, how quickly it evolves. And then there's a Hertzsprung-Russell diagram that we'll talk about that plots that temperature and that luminosity. It's plotted on this diagram. And you'll get to see how that diagram is a very, very powerful tool in astronomy to determine what stage of evolution a star is at. So that's what we're going to talk about tonight. The chat part of it, for the next 35 minutes, the order of topics that will be discussed. I'm going to give you a little bit of an appetizer, a whet your appetite. And then we're going to talk about, in particular, how stars are classified. We're going to introduce the Hertzsprung-Russell diagram, also known as the HR diagram. Then we'll talk about stellar evolution. And then part 4 will bring it all together. All those subjects are going to bring together into one nice, tidy instrument. So, just a bit of fun to whet your appetite. What's the name of this star here? Betelgeuse, yeah, and there's Orion's out here. There it is here. This is the southern hemisphere picture, which you don't get to see so often. So there's Orion's belt, and there's Betelgeuse down here. So that's very common in the sky over summer. The reason I picked that out is we're going to talk about that. Now, observations, we went 2 months ago, we went on the talk measuring up the stars. We talked how to do this, and I'll be reviewing it again very shortly. But the luminosity of Betelgeuse is about 100,000 solar luminosities. A solar luminosity being the luminosity or the brightness of our sun, one sun. So that's telling you it's 100,000 times power output goes out of Betelgeuse than out of our normal sun. Its size is about 1,000 solar radii. In other words, it's 1,000 times larger than our sun. Its temperature is about 3,600 degrees Kelvin. In comparison, our sun's about 5,800. Give you an idea of the temperature. The astronomers will say, well, from that information there, we can tell you that Betelgeuse has a spectral class of M1A1. And that's what I'll explain shortly, what all that means. But from that information, we can determine what processes and conditions are going on inside Betelgeuse, just from that information, using the Hertzsprung-Russell diagram as a tool. You could also tell at what stage of the life cycle that the star is in, and of course, we're about to move on and tell you what all that means. You can tell all that, yep, it's the Hertzsprung-Russell diagram. It's the key to understanding all of that. So now I've whet your appetite. We've got all excited. I can see you start falling up the chair with excitement. Let's move on to the main meal and find out how that diagram does help. So, classification of stars. 2 main key properties that you classify stars with, as mentioned: temperature and luminosity, which is brightness. The temperature, we went over this, so I'm just going to cover it briefly. I'm measuring out the stars a couple of months ago. But if you do a spectroscopy on the star, you plot yourself out the spectral energy distribution graph, like yay, and then you can get a crude idea of the temperature of the surface of the sun by picking off that graph, sorting out the maximum wavelength, which from here comes down to here at 500, and so on. That gives you, there's a formula for that, but this gives you a crude idea of the surface temperature of that star. Then if you want to get more fancy with that, you then have a look at all the absorption lines and features that go along this graph normally in spectroscopy. And that gives you an indication of what elements and what state of ionisation or energy levels are in this atmosphere of that star. And from that, you can refine that figure down even more. So it all comes down to doing spectroscopy, plotting the intensity versus the wavelengths, so for a nice little graph, get the peak wavelength for a clear indication, and then all your absorption lines that normally go down through there. Now, from that temperature, you then classify according to the Harvard spectral classes of stars. They come in O, B's, A's, F, G, K, M, L, and T, and there's your M for Betelgeuse in there. Now, the two things that strike me about that is, one, what's wrong with just the alphabet, guys? Whatever happened starting with an A followed by a B? Well, it's for historical reasons. Originally they did go A, B, C and so on, and it was all based on hydrogen absorption lines. And they realised afterwards, as technology got on and they developed other techniques, that was a bit redundant. So they've just kept the order, they've kept the same classes but just rearranged the order. The second thing you might say, well, how am I meant to remember that? There's a few mnemonics floating around. A popular one is, oh, be a fine girl or guy, kiss me like this. So that's a very common one. There's another one too, like old bad astronomers forget good mnemonics is another one too. I think there's in the lecture day video series they talk about that. So that's it. There's a little mnemonic to remember that. This is going down here. Here's your O, B, A, F, G, K, M. And you see they've labelled it here, there's your roughly your surface temperature corresponding, and it corresponds to a colour, intrinsic colour. And that's used a lot in astronomy, which you'll see. And remember we talked about those prominent absorption lines, and there that's the absorption lines that you would see in a star. That correlates to the surface temperature, and from there you label it an O, B, A, F, G, K or M star. Each of those classes is then further divided into 10 numbers, 0 to 9. Moving up. For example, our sun is a G2 star, for example. You can get a B0 right through to a B1, 2, 3, right through to 9, you can get an M. So each one of those is then broken down with a sub-number 0 through to 9. So that's the temperature. Then they measure the luminosity, which is the total power output, or the amount of energy per second irradiated by that entire star. And the way you do it, of course, is you get your apparent magnitude, how bright it looks like, you find out what the distance to that star is, you work out the real absolute magnitude from there. There's a little formula, that's the absolute magnitude times 4 pi squared, which of course that is the surface area of the sphere. So that tells you what the luminosity is. And luminosity is also expressed as a function of solar luminosity. Hey, Greg. Good to see you. So, and then they split the luminosity or brightness into 6 main classes. 1A, 1B, 2, 3, 4, and 5. You're already getting a bit of a sneak preview of the Hertzsprung-Russell diagram here with the plot of the spectral classes along here, the luminosities here, and you can see the particular groups of stars. And here's your big ones, your really intensely luminous ones, 1A, then you move down to 1B, move down to 2, 3, 4, 5. And as you'll find out, the stars do fit into these little groups, and each of these groups usually have a standard luminosity, and there's your classes there. So, for example, our Betelgeuse, well, you know what an MA is now, it sort of has a surface temperature roughly about 3,600 degrees, and the 1A means it was really, really, really bright, superluminous. And indeed, that's a red supergiant sitting up here. Our sun is called a spectral class G2V, and that means the G2 sort of means it's got a surface temperature of just a little bit below this, and it works out at 5,800 degrees. And the 5, meaning it's fitting in this group of luminosity class here, which is, as you'll soon find out, is on the main sequence. So those are sort of two examples there of what the spectral class actually tells you about the colour, the temperature, and the luminosity. And from there, you can plot that on your graph and you get a lot of information. So that moves on then from that temperature and luminosity. We move on to part 2. Let's have a look, a sneak preview at the Hertzsprung-Russell diagram. And you'll see there's 3 basic features that you can see on it. It's a plot of luminosity versus temperature. Stars are seen in concentrated groups, and those groups reflect different stages of evolution for those stars. So let's have a look at it. So here's your plot, here's your luminosity, and here's your temperature. Both are in a logarithmic fashion. The luminosity starts at a really low luminosity, from 10 to the minus 5 solar luminosity, really, really, really faint, and it goes right up 10 to the power of 6 solar luminosities, in other words, 1,000,000 times as bright as the sun. So that means, whoa, that gives you an indication of the huge range of power output by stars. Massive. Then we put here your temperature and your spectral classes, as you know, just match up beautifully with their colours and with their spectral and their surface temperatures. That's logarithmic as well, but also you'll notice, interestingly enough, they put hot over here and cold over here. They did that on purpose to make sense. When I say they, it was 2 astronomers by the name of Hertzsprung and Russell, interesting enough. About 1910, both of them independently at the same time came up with this idea. Should we plot luminosity versus temperature, we could make a lot of sense out of this just a jumble and zoo of stars of all different types. And sure enough, it did. Nice, beautiful little groups. So that's your x-axis, your temperature, y-axis luminosity. It's in logarithmic scales to put the large ranges in, and you've got hot here and cold here. That really leads to 2 key observations that we talked about. You can see there's clear illustrations here of concentrations of stars with a common luminosity correlations. For example, there's a nice big path up here called the main sequence we'll talk about. There's another little group of stars called giants here. Once again, all with similar correlations between the luminosity and the temperature. And you've got your supergiants up here, your white dwarfs, and so on. And each of those groups represent different stages of their lives, as I've already alluded to here. These guys here all make a nice little pattern. You're going to learn all about the main sequence shortly. These guys here, these little groups here, these groups here, they're all at the same stage of evolution during a star's life. So let's move on now to stellar evolution. Just a little bit statement about the scope, what I'm going to cover or not cover, more to the point. I'm going to start at the main sequence when stars start fusing hydrogen. It's a whole talk on its own to go over pre-main sequence stars and protostars and so on and so on. So let's keep it simple. Let's start off with the main sequence. And I'm not going to talk about stellar corpses much, black holes, white dwarfs, neutron stars, and supernovae. So that's a whole talk later on in the year to talk about those. 2 key principles with stellar evolution. First one here, I put 3 asterisks beside it. If you go away from today and only remember one single item, remember this one. It's a star's mass that determines how quickly it evolves down through the different stages of stellar evolution. That one there. So if you fall over on the way home and knock your head, as long as you remember this in the morning, it's all that matters. Don't want you to do that. Secondly, the principle is stars age and evolve, because they're full of fuel, they've got nuclear fusion going on. What happens with fuel? Fuel runs out and changes, and internal conditions change. And that's what drives stars to age and evolve, as their fuel and their internal conditions change. Two key principles. So there's 4 stages of stellar evolution, starting at the main sequence, that is. So the main sequence, which we're going to talk about, then we'll discuss the red giant stage of a star's life. We'll then talk about the horizontal branch stage of a star's life. And then, depending on its mass, and that's the whole thing of this talk, everything hinges on the star's mass. The mass is the DNA of the star. If it's less than 8 solar masses, a solar mass being the mass of our sun, it's about 2 times 10 to the 32 kilograms. In other words, 2 with 32 zeros after it. If it's less than 8 times the mass of our sun, it goes down a branch called the asymptotic giant branch. And eventually it ends up as a white dwarf in a planetary nebula. Or if it's greater than 8 solar masses, it implodes into a neutron star or a black hole with a big, nice big fancy supernova. So those are the stages we're going to briefly talk about. So the main sequence, so you've got this big sphere of gas and dust that's been busy contracting down in its infancy. It gets hotter and hotter and hotter and higher pressures inside the core. And eventually the core hits about 15 million degrees Kelvin. At that stage, the protons, which is the hydrogen nuclei, which is just positive protons, they're zipping around so fast enough, ramming into one another, they can just start to overcome that same positive electrostatic force, the same force that's repelling them. They can overcome that, and as we spoke about last month with the talk on solar neutrinos, with a little bit of help of some quantum tunneling, the process starts to proceed, and you start getting hydrogen nuclei, which are just wall proteins, fusing together to form helium, just 2 protons and 2 neutrons. We mentioned a little bit of detail last month on that. If anyone wasn't here for last month and they want those details, I deliberately put my email at the top, I think that first paragraph. Just send us an email saying, hey, I wasn't here last month. There's a damn good excuse why you weren't here last month, but I wasn't here 1 month ago, and I'd be interested in that handout just to bring myself up to speed, and that's absolutely fine. Or you've got any questions for that matter either. So hydrogen starts turning into helium, and by definition your star is now on the main sequence. Yeah, I'm a star, it says. So what happens during the state? It's a state of hydrostatic equilibrium, which means that the inward pressure of gravity, of the mass driving it in, is perfectly balanced by the force, the pressure outwards of nuclear fusion going on. So that nuclear fusion, as you imagine, you can see nuclear bombs, they deliver a lot of power. It's all going on in the core, and the star settles down into a state of hydrostatic equilibrium, whereby the outward pressure of those nuclear forces perfectly matches the inward drive of gravity. A star sits very, very stable there. It will spend 90% of a star's life will be sitting in that state there, hydrostatic equilibrium on the main sequence. So you've probably heard our star last about 10 billion years in the main sequence. So that immediately tells you when it's done and dusted there, the remainder of its life is going to be just a quick billion years, so 10%. Key principle, bigger the mass, higher pressures and temperatures, burns fuel a lot more quicker. And a good analogy, you have a rip-roaring bonfire, raging away, and you throw a log on it, 10, 15 minutes, that log's just burnt up. When you go to bed at night, you let the fire go down a little bit, just to keep the house a bit warm, and for the morning you throw a log before you go to bed and put a screen over it and stuff. Get up next morning, 8 hours later, that little log is still just quietly smouldering away. It just doesn't burn so quickly. I use that analogy for metabolic rates too. Everyone should have breakfast, single most important meal of the day. Get that metabolism roaring. Anything else you eat for the day will just burn up. Versus if you starve yourself and metabolic rate drops right down, everything you eat just turns to this stuff here. Another little analogy that I use day to day. So bigger mass, higher pressure and temperature, burns fuel quicker, and that's what it's all about. They have big stars, burn out quickly, have big, great, big, bright, flashy lives, but burn out quickly. Much like Hollywood stars.